Hi there. Today we're looking at Do ImageNet Classifiers Generalize to ImageNet by Benjamin Recht, Rebecca Roloffs, Ludwig Schmidt, and Vaishal Shankar. So the premise of this paper is pretty simple. We've been training models on ImageNet now for a while, almost 10 years to be exact. ImageNet is this data set with a lot of images, millions of images, categorized into many thousands of categories. Now the classic part of ImageNet that people know has about 1.5 million images in 1,000 different classes. And this ImageNet was one of the main data sets now, or has been for the last few years. And as you can see on the right here, the error rate year after year was pretty much, I think, cut in half every year since 2012. When the first net, AlexNet, was using deep learning instead of the classical computer vision approaches. So we've been training on ImageNet for a while, and the idea or the question this paper asks, if we collect a second test set, right? So for ImageNet we have a train and a test set. If we now collect a second test set here, test v2, right? If we have a model that was trained on training here and evaluated on test, does it also perform well on this second test set, right? The idea of this being that maybe over the years we've tuned our hyperparameters and all such that the models perform well on that particular test set. Let's call this V1, right? And it might not be as successful on a new test set. So this paper goes about collecting a test set to ImageNet in exactly the way that the V1 test set was collected, right? So they try to match exactly the process of how V1 was collected to create another test set, and then they evaluate models on that new test set. They do this not only for ImageNet, but also for CIFAR-10, which is a much smaller data set, but also a lot of computer vision algorithms are evaluated on CIFAR-10. So let's just put up a hypothesis here. The hypothesis is that we have pretty much overfitted to ImageNet by now. This is a very prestigious number to get if you have state-of-the-art on ImageNet, and therefore tuning your hyperparameters and your learning rate and everything such that it performs well on the test set V1 is very likely. So this paper has the most important plots are like this. It has two axes, and on the bottom axis is the performance on V1, right? And so performance, and that means accuracy, basically, so accuracy. And on line 2 is V2 accuracy. Now, here is 1, here is 0. This line here means that if a model is performing 50% accuracy on V1, it is also performing 50% accuracy on V2. So being on this line would basically mean we have not overfitted, and the model is performing equally well on both sets. So what now if we assume that we have overfitted? If we have overfitted, we would assume that, you know, the models that perform really poorly might also, you know, they perform they're not really overfitted. But over the years, as we've gotten better on V1, we stray away from this. So we get better on V1, but we don't really get better on V2, right? And that means we've overfitted to V1. And this might even go down, right? The more we might overfit to V1, the worse we're actually going to get on V2. So this is kind of a meta overfitting. So this is what we would expect if we overfit, right? Overfit to V1. And I think this was the initial hypothesis behind the people that ran this experiment to check, can we see an effect like this, or is the effect more a continuous one where we don't overfit? And what they found was neither. And these are basically these interesting plots here. So again, the dashed line here would be the not overfitting line. So what they find, if you, for example, look at ImageNet, every dot here is a model, right? So this model right here is performing with like a 67% accuracy on V1, and it is performing with something like a 53% accuracy on V2. Now, if you look at this line here, what that means is every model kind of drops by about this much, right? So we don't see this and we don't see this, but we see this line is shifted down. And if you look closely, especially on CFAR10, you can see the line, rather than being tilted like this, is actually tilted a bit slanted upwards, right? So the angle is higher, is greater, the slope is greater than the 1-to-1 slope. This is extremely interesting. If you think about what does that mean, it means that if you take a model, right here, if you look at its order, let's look at this model here. This model is number 1, best model in the world, right? It will still be number 1 on V2. This model here is number 3, rank 3 on V1. It will also be rank 3 on V2, right? So the order of models is pretty much constant. So if a model is doing well on V1, it is also doing well on V2 in relation to other models. But every model experiences this drop in accuracy. And the most interesting part is that, and again you can see this more here, the better you're doing, the smaller this drop gets, right? This drop here is smaller than this drop here. This is exactly counter to the notion of overfitting, where it seems the more accurate you get on V1, the more you're able to close this gap between V1 and V2. And if you extrapolate here, you might as well think that once we are or actually, sorry, 100% is already here. If you could go higher, maybe. Or maybe you can see here that in the end, these will actually converge. But nevertheless, if the models that are doing better on V1 aren't only not overfit, but they are actually experience less of a drop with regards to a new test set. So they generalize better to the new test set than the worse models, right? And that is crazy. And it is not only neural networks, right? So up here, you have the deep neural networks and whatnot. But you can also go with, I believe some of these, or even further down here, are k-nearest neighbor classifiers and things like this. So it doesn't seem to be a property of neural networks. It really seems to be a property of the data set. And this paper, first of all, goes over how they collected these. And second of all, their hypotheses and investigations into why this phenomenon exists, why we are all of a sudden worse on the new test set, but completely worse in a different way than we expected compared to the original test set. All right, so they first say potential causes of accuracy drops, and they propose a model. They say here is the entire difference between two data sets with regards to a classifier. It can be decomposed into 3 different gaps, and you see the first and the last part here are the ones from the left side. So this is an expanding sum in the middle. So there is the generalization gap. The generalization gap refers to the gap that you have between different data sets of the same distribution. So this is like, you know, from the train versus test set. You train on the training set, and then you have a generalization gap to the test set. In this case, the generalization gap simply refers to the difference between the generalization to the first and to the second set. They argue that this isn't really an issue here because they can put up confidence intervals. So if those were identically distributed, how much would the generalization gap be at maximum given some kind of confidence interval? 95% confidence interval would only give you plus minus a 1% difference in generalization gap. So they rule out that this is the reason for the big discrepancy. Then have two others. They have the adaptivity gap and the distribution gap. So the adaptivity gap is what we hypothesized at the beginning. It is the overfitting to the first data set or to one of the two data sets. So if you have a big adaptivity gap, then you have fitted much more to one than to the other data set. Now, because of the shape of the curve being the way it is, they also rule out the adaptivity gap. And we went over why, right? Because it would look completely different than it does. Now, the only thing remaining here is this distribution gap. So they explain that this difference here most likely comes from the fact that the old and the new test set have a different distribution. And they go into why that is. And I'm going to compress their sort of hypothesis of why that is into a short summary, let's say. We won't go over the entire paper. They basically say that the mechanical Turk the mechanical Turk part of the processing pipeline has a very big influence. So what happens when you collect an ImageNet test set? You start with Flickr. This is a big image database, and the images, as far as I can understand, they are tagged and you can search for them and so on. So they start by going to Flickr and searching for images, and their ground truth class labels come, you may know this, from a system called WordNet. And WordNet is sort of a linguistic classification of words into groups. So it would have hierarchical, it would have animals, animal being a word, and then below animal it would have dog, and then it would have terrier, and it would have these hierarchical groupings of these words. And they search on Flickr for images, and then they put the images to a human rater. So the human rater on a system called Mechanical Turk, you may know it, that you can just sign up there and do these kind of tasks. They present the human with a grid of images and a class, terrier. And they say, please select all the images where a terrier appears. So the human might select this, 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 and this one, right? And that will give you what they call a selection frequency. So selection frequency. So how often was a particular image selected given that class? And of course, the higher, so you do this over many, the selection frequency is across many of these Mechanical Turk workers. So if for a given image, the selection frequency is high, let's say going towards 1.0, that means every single human selected that image to be in this class. So you can be pretty sure it's in the class. If it goes towards 0, then you can be pretty sure it's not in the class. And this selection frequency criterion, the paper thinks that this is the main criterion why the data sets are of different difficulties, let's say, because even though they try to match the process exactly, even what the questions they posed to the Turk workers, they even restricted their flicker date range to the date range where the original ImageNet was collected. They still think that there is a difference in how the mechanical Turk workers basically rated the images, or then after that how they were selected using the selection frequency. So what they do is they select different images depending on criteria so they can test these hypotheses. Their original V2 test set is called matched frequency. Now what you do in matched frequency is you kind of play a little game. What you do is every now and then you will implant an image here of the V1 test set. So thereby, and of the V1 test set, either of this class or of another class. So you can kind of do a quality control. From this, you can now find out what is the selection frequency of images in the V1 class for Terrier. And then you can simply select the same one in the V2, right? So if you know the selection frequency for V1 was 0.8, you can just put the threshold here at 0.8, and you know you can be reasonably sure that you have selected a similar difficulty. Or so you would think, right? So if they do it like this, then they get this drop that you saw at the beginning. They also do this threshold 0.7, which I guess is arbitrary-ish. And then they also say top images, where they say, for each class, we chose the 10 images with the highest selection frequency. So these would be the sort of easiest ones. And if you look at the graphs, and this is ImageNet, for these different data sets, so if you do the threshold 0.7 that they selected, now the old line was somewhere here. Now the new line is much closer, right? You see that here. And if you do these top images, so you just select the easy ones, the new line is actually above, right? This is now, note that the red line here is above the black line, while here it's below. It is still extremely interesting that still there is this almost linear relationship between the V1 and V2 accuracies. And even here on this easier data set there is. So they basically hypothesize by thresholding differently for the new data set, you have a very good grip on the difficulty of the new data set. So this process of matching the selection frequency, so this matched frequency data set, it might actually not result in the same difficulty in data set. They do have some more experiments where they experiment with different difficulties. So let's actually jump down there. It's a bit of a jump because there are over 70 pages in this paper. The appendix has its own content directory. That's how crazy that is. But I want to show you these plots. So here, what they do is they do different bins of this set. So they have bins of easy samples, less easy samples, and so on. And you can see that you have a pretty good grip on this, where this line is. So if you only take the easy samples, you're up here, and this is about what we saw before. If this is the old line, it's the red line, right? If you take the entire new test set, if you just take bin, the second hardest bin, you're somewhere here or here or here. So you have a good hold on where this line is. But that still doesn't explain that if you try to follow the protocol exactly, why does the accuracy drop? That is still a mystery. Even though they say here is a variable that influences this a lot. If they try to set the variable as it was set in V1, it is not equal. So still mystery remains, I would say. So the last thing they do is they try to just come up with a model for this. So their hypothesis now is that the new test set just is harder. And they have a analytical kind of a formal model of why, if you assume certain things, this results in this line, right? The really interesting thing about the paper is that the accuracies, they all fall exactly on this line. There's this linear relationship, especially they say if you do like pro-bit scaling of accuracies, there's this line. And so they put up a model where you say, what if we assume that each example I has a difficulty, right? It's just a number how difficult it is. And each model J has a probability of correctly classifying an image with difficulty tau here, given by this function, right? So this here is the probability that the model will classify an image correctly, giving that it's tau hard, right? And so this is an increasing function, and they put up this following parameterization. This is the CDF of the, so they've put up a model for this function now, right? For this, they say, if we assume that it is like this, that each model has a sort of a skill number. So each model has a skill, and each image has a difficulty that is tau. Now, if the skill is higher than the tau, probably it will classify correctly. If the skill is lower, probably then this number is negative, it will classify it incorrectly. So this is the CDF of a normal distribution. It goes something like this, right? And if the 0 point is here, so if this number here is 0, it's like 50-50 whether it will classify it correctly. So if you assume this, and you assume a bunch of other Gaussian error distributions, then the performance of a model on the test set V2 is exactly the performance of the model under test set V1 times this scalar here plus this scalar here, which is a linear relationship. So they put up a model for this. Of course, this doesn't explain anything, right? This doesn't explain the phenomena, but it still gives a clue of why the linear relationship here might result from the test sets having a different difficulty setting, or a different difficulty properties. So they go on, after discussing related work, they go on to say what can one do, and suggestions for future research. I especially like the super holdout. So if you ever make a data set, then make a super holdout set, and once you're like almost out of your career, just come up with it and say, oh, I have this lost data set here that I made way back. It will be fantastic. All right, so I think this paper is very interesting, and I think everyone that sees and reads this comes up with their own hypotheses of why this is and what's going on here. They have investigated a lot of this. Especially I want to highlight an experiment where they taken part of V2 here. So they split this one into a train and a test. Train and a test. And they put this and this training together into like a super train, right? So you train on both things together, and they see whether it improves at this test set, right? You would think that if you put this training in there, that it would improve, and it does improve, but it improves by like a minuscule amount. So they've done a whole bunch of experiments like this to investigate what's going on. This is all in this 70-page appendix that you can go over. Right, that was what I had to say for this paper. If you like this video, consider subscribing and comment what you think. I usually answer or like or read most comments. Thanks for listening. Bye-bye.